Section 2.5, determinant and multiplicative inverses of matrices. We're going to start with a vocabulary term here. That would be determinant. It's basically a number that can be used to describe a square matrix. We're not really going to use determinants to describe it, other than we're going to need to find it here for what we're going to be doing in this section. Okay, so if you're asked to find the determinant, you're going to be asked, or it's going to look multiple different ways, or it could look at multiple different ways. So if you're asked to find the determinant, it's either going to say det of the matrix, so we could say 3, 0, 5, 9 for a square matrix. Key here is it's got to be a square matrix. If it was a 2 by 3, then it wouldn't have a determinant. It wouldn't be possible to find. Or what we could see it as is it could look like absolute value brackets of the same matrix, or any square matrix. So 6, 7, -3, 11, for an example. Those are two different ways that you could be asked to find a determinant. If the matrix is named, so let's say A was equal to some matrix, it could say find the determinant of A, and I've got that down here below here, and we'll get to that here in just a second. So let's let A be equal to a square matrix, a 2 by 2 square matrix. So oops, we go back to the pen here. Call it A, B, C, D. It really doesn't matter what your elements are, but as long as they're labeled, that way I'm labeling them so you can see what needs to be, or what's going to happen to find the determinant. The determinant of A is equal to, what we're going to do is we're going to take this main diagonal here, AD, we're going to multiply those two numbers together, and we're going to do the same thing with the other diagonal, BC. And what we're going to do is we're going to subtract them. That is how you find the determinant of a 2 by 2 matrix. You take the main diagonal from top left to bottom right and multiply those numbers together. You do the same thing from top right to bottom left and multiply those together, and then subtract those two numbers with the red minus the blue, at least in my case where I've got it written on here, and that's going to be your number. It's a singular number. It's a value that we're going to use later on. So I got a couple of examples here. Find each determinant. So I got 8, 4, 7, 6. It's a 2 by 2 matrix. We're going to take the main diagonal. Before I do that, I'm going to write the determinant. We're going to call this A. This is equal to A. So we're going to say the determinant of A, or determinant of our matrix A, is equal to, we're going to take 8 times 6. We're going to take our main diagonal. We're going to do the other main diagonal right there. We're going to do 7 times 4, and it doesn't really matter what order you write this in. You could go 4 times 7, you can go 6 times 8, it really doesn't matter. And we're going to subtract those two numbers together. 8 times 6 is 48, 7 times 4 is 28. We're still subtracting here. 48 minus 28 is equal to 20, and that would be our answer. It's just a singular number. The determinant of that square 2 by 2 matrix is 20. Let's try another one here. Now, this time I've got the absolute value bracket, or what looks like absolute value brackets, so we don't necessarily need to do this part. This is already telling us that we need to find the determinant. So let's go ahead and do that. We're going to take our red diagonal, so we're going to take 0 times -6. We're going to subtract the other diagonal, 8 times -2. This time I went from left to right. It doesn't really matter what order you write them in. And let's see, let's multiply these together. 0 times 6 is 0. -8, or 8 times -2 is -16, and I am still subtracting them, so 0 minus -16 gives me positive 16, and that's all there is for finding a 2 by 2 matrix determinant. For a 3 by 3, it's a little more complicated. Okay, we're going to rewrite the first two columns on the right, find the sum of the three down right products. I'll show you what that means. That would be like these red ones, down and to the right. Find the sum, that should be the, not 5. I don't know, that was autocorrect on my iPad here. So find the sum of the three down left products, so that's this way. That'd be the blue ones up here. And then we're going to subtract down right minus down left, just like we did up here, but now we're going to have multiple numbers that we're going to be adding and subtracting. So the determinant of, I've got a 3 by 3 matrix here, A, B, C, D, E, F, G, H, I. Okay, I'm going to rewrite this into, use purple here. I'm going to use the bracket, the absolute value bracket. So I'm going to have A, B, C, D, E, F, G, H, I. It's a really bad G. G, H, I. And then I'm going to do the steps here. So it says rewrite the first two columns to the right. So I'm going to do that part in orange. So we're going to rewrite the first two columns. So A, D, G, and then the next column was B, E, H. Now, the determinant of this is going to be equal to, we're going to take our down right product, so that's AEI. So I'm going to lump these together. AEI, that's my first one. I'm going to do the next one, just keep going to the right, BFG, and we're going to add these together, BFG, And I got one more downright product. That's CDH plus CDH. There's my 3 downright products. Now I got to do my down left products. So I'm going to start with CEG. So I get CEG. And then I've got another one here, AFH plus AFH. And I've got a third one here, BDI plus BDI. There's my 3 down left products. And then I'm going to subtract them in the very end, and that will give me my 3x3 determinants. A little more complicated, a little more labor intensive, but still very, very doable. So let's try a couple here. Find the determinant. -4, you can read it there. I'm not going to read it to you. Let's go ahead and write this out. I'm going to go ahead and write out my 2 columns to the right. So I'm going to rewrite the first and second column. So -4, 5, -2, and then -6, -1, 4, and then I need to find my my diagonal products. So I'm going to start with my down and right ones. So that's -4 times -1 times -3. 3 negatives gives me a negative. 4 times 1 times 3 is 12. So I got -12. Then do the next one. 6 times 3 is 18 times 2 is 36. I've got 2 negatives, which makes that a positive 36. If you ever get a negative when you do your product, then the sign in front of it just becomes a minus. Then I got one more. 2 times 5 is 10 times 4 gives me 40. And I've got my 3 downright products. Now I know I'm going to subtract. And now I'm going to do my down left product. So I'm going to take 2 times -1 times -2. 2 times -1 is -2 times -2 is positive 4. Do the next one. -4 times 3 is -12 times 4 is -48. So it's going to be -48. And then I got one more. -6 times 5 is -30 times -3 is positive 90. When we do this, let's see, go to purple, equals -12 plus 36 plus 40. When you do that, I'm assuming you're going to do that in the calculator. I don't blame you there. That's 64. We're subtracting 4 minus 48 plus 90 is 46, and 64 minus 46 gives us 18. So the determinant of that 3x3 matrix is 18. Let's try another one here. If you want to pause the video and do this on your own and then try it, feel free. I'm going to kind of walk through this one just a little bit quicker. So I'm going to rewrite my 2 columns, 5, 6, 0, 3, 4, -3. Go right into my down left products. 5 times 4 is 20 times 7. Let's see, 20 times 7 is 140. 3 times 8 times 0, that's real easy, that's 0. 1 times 6 times 3 is 18, and it's positive 18. And then I'm going to subtract, got my down left ones. 1 times 4 times 0, that's easy. 5 times 8 is 40 times 3 is -120. And 3 times 6 is 18 times 7 is 126 plus 126. I did that in the calculator already, so don't think I'm that good. Let's see. 140 plus 18 is 158. And let's see, I should have written that in red. Oh well. Minus -120 plus 126 is 6. 158 minus 6 is 152. So you get 152 for your determinant on that matrix. What we're going to use the determinants for is kind of using 2 different types of other matrices. It's going to be the identity matrix and then the inverse matrix. The identity matrix is a square matrix where all the elements are zeros except for the diagonal from top left to bottom right. And those elements are ones. So if I have a 2 by 2 matrix, the identity matrix looks like this: 1, 0, 0, 1. Okay, a 3 by 3 identity matrix would be 1, 0, 0, 0, 1, 0, 0, 0, 1, where all the elements are zeros except for that main diagonal from top left to bottom right. If you wanted to draw out a 4 by 4, I don't know if I have enough room, but we'll give it a shot. So it would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. That would be a 4 by 4 identity matrix. Okay. What we're going to be focusing on, where this is going to come into play, is when we get into the idea of inverse matrix. A square matrix A, and this is pronounced A inverse. I'll write this up up above this. So this is A inverse. That's how you say this. A inverse is the inverse of another square matrix A if and only if. Now remember, when we talked about multiplying matrices, we said the order in which you multiply matters, because remember, those inside 2 numbers have to be the same. Okay, so, and we've seen it before where AB is going to be different than BA when we're talking matrices. Now, if it's just two numbers like 3 times 2 and 2 times 3, yeah, that the order there doesn't matter. The order in which they're written doesn't matter. But when we're talking matrices, it definitely matters. So, an inverse matrix, a square matrix A inverse, is the inverse of another square matrix A, if and only if. Here's the key. If we take our original matrix A times A inverse, that has to be the same as A inverse A inverse times A. Those two products have to be the same. And what you're going to get with both of those, what you have to get is I, which is the identity matrix. You have to get one of those in order to prove that a certain matrix is an inverse of another matrix, okay? So if A inverse is in fact the inverse of A, when you multiply A and A inverse together, no matter which direction you go, you get the identity matrix in return, okay? And I'll write this off to the side. This is the identity matrix. Identity matrix. That's what I stands for, is the identity matrix, okay? So inverses are kind of difficult to find. I don't want to say difficult. They're tedious to find. I'm going to show you how to do 2 by 2 by hand. 3 by 3s, you can use your calculator to find those. If you look, I'll show you in class how to find the inverses of matrices on your calculator. I'm sure you'll be able to figure it out on your own if you just take 2 minutes to try to look around your calculator and see what happens. But I'm going to show you how to do it by hand for 2 by 2, and then we'll leave it there. So, finding inverse matrices for 2 by 2. If A is equal to, so I'm going to start with a general matrix. So we're going to have A, B, C, D, remember 2 by 2. And the determinant of A is not equal to 0. That's a key word, or key part of this. The determinant of A cannot be 0. Then, what we can say is A inverse, the inverse matrix, is equal to, we're going to take 1 over the determinant of our original times another matrix, a different matrix. We're going to manipulate these 4 original elements in this new 2 by 2 matrix. It's going to become D and A switch places. The diagonal here switch place. And then the other diagonal, C and B, they stay where they're at, but they switch signs. Okay, so this is going to be negative B in the upper right-hand corner and negative C in the upper left, or lower left-hand corner. Sorry, lower left-hand corner. Okay, so that's, we're going to take the inverse, to find the inverse, we're going to take 1 over the determinant of the original, so we're going to have to find that number that we did at the beginning, and then we're going to multiply that, so we're going to use scalar multiplication. We're going to flip the main diagonal around, we're going to flip the signs on the other diagonal, and we're going to distribute. Honestly, once we come up with our determinant of A and we move these things around, if you want to leave it like that, I'm okay with that. The book allows both. You can write it like this, or you can actually distribute it. Most of the time, it's not going to give you great numbers. And I'll show you here in a second what that could look like. It might look really, really messy. So if you want to leave it as 1 over something times a mixed up matrix, that's fine. If you want to distribute it, that's fine too. So let's try a couple here. Find the inverse of each matrix. So we'll start with number 1. First thing we need to do, I'm going to label this just as A. This is my original matrix, so I need to find the determinant of A first. That's really the first thing you need to do. So the determinant of A is equal to, and we'll do our diagonals here, so we'll do 8 times negative 1, and then we're going to subtract, we'll do the other diagonal, 9 times 3, whoops, 9 times 3, and let's see, 8 times negative 1 is negative 8, minus 9 times 3 is 27, and what we're going to get when we find our determinant, negative 8 minus 27 is negative 35, okay? Not terrible. So now we can go into labeling A inverse. So A inverse is equal to, remember we said it's 1 over the determinant of A, so we're going to have 1 over negative 35, or just negative 1 over 35, times, now we need to rearrange our original elements, and you can see the main diagonal switches elements, so this 8 and negative 1 are going to switch places, so negative 1 now is upper left, 8 is lower right, and the 9 and the 3, the upper right and lower left, they stay in the same place, but they switch signs. Okay, so the 3 becomes a negative 3, the 9 becomes a negative 9, and if you want to leave it just like that, I am okay with that. The book is okay with that. If you want to distribute this out, feel free. You're not going to get great numbers. If you can simplify, please do simplify. This one, though, you're not going to be able to simplify. A inverse is equal to, so this becomes negative times negative is actually a positive, 1 over 35. and this becomes 3 over 35 lower left. Negative 9 times negative 35 is 9 over 35, and then this becomes negative 8 over 35. This would be an example where I would probably leave it like this, just because, you know, these aren't great numbers. I do need to close my bracket there, but either one of those is fine. I don't really care. Either one, like I said, is going to be good for me. So let's try another one here. We got 2, negative 3, 4, 4 for our 2 by 2 matrix. This is A again. We need to start by finding the determinant of A. And again, I'll draw my diagonals here, 2 times 4. And then our other one, negative 3 times 4, or 4 times negative 3. And this is going to be subtracted. 2 times 4 gives me 8. Minus 4 times negative 3 is negative 12. 8 minus negative 12, that would be positive 20. So there's our determinant. So now to find our A inverse is equal to, we're going to take 1 over our previous determinant, 1 over 20, times, now we're going to mix up our original matrix. The red diagonal switches places, so this becomes 4 and 2. And the other diagonal, the second diagonal, you can call it, I don't really know if it's got a real name, an official term. These two numbers, these two elements switch signs. So this is going to become negative 4, this is going to become positive 3. So we'll flip that, negative 4, positive 3, and there's that. Now again, if you want to leave it just like that, feel free. If you, whoops, that's supposed to be split up. If you want to distribute that, use scalar multiplication, you certainly can. Whoops, this is going to be A inverse is equal to, this is one though where you will have to simplify. 4 over 20 does simplify into 1 over 5. Again, same thing with negative 4 over 20 is negative 1 over 5. Let's see, 3 over 20, that one doesn't simplify. And 2 over 20 simplifies into 1 over 10. So that would be an example where you do simplify it. Those aren't terrible numbers, but again, not the greatest of numbers either. How we're going to use inverse matrices is to solve system of equations. And it's really kind of neat how this works out. So how this sets up, the coefficients of x and y make up a 2 by 2 matrix, and that's matrix A. So I'm going to do that in red. So my coefficients of x and y, so that's going to be 2, 3, 1, and negative 1 in this case. This is matrix A. The variables make up a 2 by 1 matrix, and that's matrix X. I'll do that in we'll do that in orange. So A times, we're multiplying here, A times my two variables x and y. That's matrix X, and they make the answers make up a 2 by 1 matrix as well. So this is equal to a 2 by 1 matrix. We'll do this in blue. The 2 by 1 matrix this time is negative 17 and 4. Okay, this is matrix B. So how this works, how we're going to solve this equation, how we're going to solve for x and y, we're going to multiply both sides of this equation by A inverse on the left. And again, it's important that we do this in the proper order. We've got to do it on the left, because if we do it on the right, then it all gets screwed up. We've just got to make sure that we do it on the left. And let me kind of explain why. So we've got our equation AX equals B. And we're going to multiply by A inverse on the left. And what happens when I multiply by A inverse on the left? So I got A inverse, then I got AX is equal to, I'm going to put A inverse in there again, A inverse times B. Okay, I'm multiplying by A inverse on the left on both sides. A inverse times A, remember A inverse times A is equal to the identity matrix. Basically that's 1. Whoops, let me go back, make that red, a red X. And this is still equal to A inverse times B. And like I said, the identity matrix is basically 1. If you multiply the identity times anything, you're going to get this, whatever this was. Okay, so what happens here is we can kind of ignore this this identity, because it basically goes away. So our variables, because remember x was our variables, is equal to whatever the product of these two are, and that will give us our solution to our system. So we can really use our calculators without graphing, without using substitution, without using elimination to solve a system that maybe we wouldn't want to otherwise. So I got a couple of examples here. I'm going to go ahead and I'm going to tell you, use your calculators for these. What I'm going to want to see, I'll show you in these two examples in terms of like quizzes and tests. But really, we're going to be using our calculators here to simplify our lives. So number one, solve the system here. 2x plus 3y equals negative 17, x minus y equals 4. That's what this one is right here. We're just going to go ahead and actually solve this system. So We'll write our matrix equation again. So we'll have 2, 3, 1, -1. And I'm just going to do this all in one color times xy equals -17 and then 4. And again, this is all calculator work. So this is going to be A times X equals B. So we can say that X is equal to A inverse times B. Now you do have an inverse button on your calculator. It's actually the main button for matrix. So really, if you can type in A and B into your matrix functions on your calculator, you can do this right away without even having to know what how to do the determinant or everything is. And I'm telling you, use your calculator here. What you're going to find then is that X is equal to, so our identity matrix, remember, is XY. That's going to spit out a matrix of -1, -5. And what that tells you is that the solution to this system is -1, -5. So X is equal to -1, Y is equal to -5. So the calculator can save you a ton of time to do these types of problems where you don't have to do elimination, where you don't have to do substitution, you don't have to graph anything. This can save you a ton of time. If you have 3 variables like we do here in number 2, the process is exactly the same. The only difference is instead of having 2 by 2s and 2 by 1s, we're going to have 3 by 3s and 3 by 1s, but it's going to be the same thing. And I'm telling you, use your calculators here to make your life a whole lot easier. So we'll make our original matrices. So we got 1, -2, 1. So our coefficients make up the first one. 2, 3, -3, and then 4, 10, -5. Times, now our variables this time, we got X, we got Y, and we've got Z. And this is equal to another 3 by 1, 15, 1, and -3 again. And again, use your calculators here. So just as long as we can identify or define A, X, and B, we can say that X is equal to A inverse times B. And again, use your calculator here. So we know that X is equal to XYZ. And that's going to spit out in the end a 3 by 1 matrix of 8, -2, and 3. So if we're going to write an ordered triple to write our official answer, 8, -2, and 3.